On July 14, 2026, Microsoft released the largest Patch Tuesday in its history. In a single update, they addressed over 570 vulnerabilities, including 3 0 days. Security researchers and Microsoft itself traced this massive volume of exploits to a specific shift in methodology: the deployment of autonomous AI for vulnerability discovery and fuzzing. These AI models iterate through codebases and identify flaws in real time. Human engineering teams, relying on linear testing and deployment schedules, cannot generate patches fast enough to close the exposure windows. By rapidly testing logical boundaries, these models learn to break software abstractions altogether. They do not stop at the application layer. They bypass Ring 0 guest operating system security policies to reach the foundational execution environment. Any defense mechanism that relies on mutable code, rules, policies, or access controls will fail when pitted against an adversary capable of executing and iterating at machine speed. Because software abstractions can be autonomously bypassed, logical trust itself is a critical strategic vulnerability for Tier 1 infrastructure. To secure high-stakes data, we must operate under the doctrine of the hostile memory environment. This requires shifting the assumption of compromise away from the network perimeter and placing it directly on the physical motherboard. Computational architecture is stratified into privilege rings. The guest operating system operates at ring 0, managing local applications. But beneath that sits the hypervisor at ring -1, which controls the physical hardware allocation for the entire server. Traditional EDR sits within ring 0, entirely blind to ring -1 incursions. This enables a silent observer attack. A compromised hypervisor can actively pause the virtual machine, siphon memory, and manipulate the virtual clock to hide the delay. Attackers achieve this through side-channel techniques like prime probe. By exploiting shared silicon resources, the hypervisor reads the state of the hardware directly, bypassing the operating system's access controls entirely. Because these attacks interact with the physical processor cache, they manifest purely as thermodynamic noise. They leave absolutely no trace in standard OS event logs. From its privileged position, the compromised ring -1 environment feeds the EDR normal system states. The security agent reports a clean bill of health while exfiltration is actively underway. When the host system acts as the adversary, defense must abandon the operating system and anchor directly into the physical laws governing the hardware. We establish that physical anchor through thermodynamics. Computation is a physical process that requires energy, meaning unauthorized observation cannot be perfectly hidden. The Vapor Audit architecture deploys a microcode sentry. This is an active background daemon executing a continuous, deterministic mathematical fold, summing integers from 0 to 1000. By locking this workload strictly within the L1 cache, the sentry completely eliminates variable latency from the external DRAM, creating an isolated timing baseline. The sentry uses the RDTSC instruction to read the physical quartz crystal oscillator, measuring the exact cycle count. If a hypervisor attempts a snapshot, it steals shared resources. This friction causes an energy shadow and slows the cycle count. We define a strict mathematical threshold. If the cycle variance exceeds a calibrated 3 sigma threshold, the system registers a thermodynamic violation. This micro-architectural detection occurs in mere CPU cycles. Traditional EDR log analysis requires millions of cycles to process, leaving an enormous window for data extraction. Under this model, sovereignty becomes a physical property of the execution environment, validated by the specific thermodynamic friction of the processor itself. We apply the same physical verification to geographic location to defeat the teleportation attack, where virtual workloads are silently migrated across sovereign borders. This is an infrastructure diagram showing a sovereignty fracture. In this scenario, standard infrastructure as code prioritized availability over compliance and redirected traffic bound for an offline Frankfurt node straight to US servers in North Virginia. To prevent this, the architecture utilizes Alibi Routing. This mechanism triangulates latency using the immutable speed of light in fiber optic glass to verify the physical location of the data at rest. Exceeding a strict 15 millisecond round-trip time threshold mathematically proves the hardware is not within the authorized jurisdiction, automatically rejecting the write request. The second physical vector is local RAM, targeted through the memory siege. Here, attackers use rapid heap sprays to fill cached memory allocator lists with malicious payloads. This schematic contrasts memory states. The top row shows a normal configuration, keeping freed pages dirty in user space. The bottom row illustrates the Vibranium defense. Setting purge delay to 0 forces a MADV don't need system call, physically revoking the page mapping. By strictly enforcing the speed of light over the network and denying persistence in local RAM, the architecture aggressively starves the adversary of both time and space. When a hypervisor detects a vulnerability, it initiates a memory snapshot. This triggers a context switch, requiring a snapshot gap of 1,000 to 20,000 cycles to lock and capture a virtual machine's memory. Any physical or thermodynamic violation triggers the fail-dead protocol, a sub-100 cycle kinetic defense that mathematically guarantees data destruction before the hypervisor can complete the snapshot. This protocol bypasses traditional compiler dead store elimination by explicitly injecting high-entropy noise, mapped as the 0xFF pattern, directly into the physical memory registers. This kinetic defense creates a collision with the federal rules of civil procedure. Under Rule 37E, destroying the keys required to access data, even to prevent an active breach, can be legally categorized as evidence spoliation. To resolve this, the architecture implements a legal interlock. This mechanical feature explicitly separates the necessary destruction of volatile RAM from the preservation of persistent ciphertext on disk. This is a structured JSON audit log generated by the kernel-level sanitization interceptor. When the interceptor reads an active litigation status, it mechanically blocks any file system deletion, categorizing the action as an authorized preservation event with any erasure aborted action. The system achieves dual compliance. It executes kinetic self-destruction to deny adversary extraction, while simultaneously generating a mathematically verifiable legal alibi for the courts. Traditional infrastructure security relies on the shared responsibility model, which assumes a level of trust in the cloud provider's logical abstractions. Physics-based execution integrity moves past these assumptions by verifying the hardware state directly. To protect the development pipeline, the system utilizes a semantic firewall. This continuous integration linter enforces a zero liability lexicon at the source code level to prevent adverse inference during future e-discovery. It maps aggressive, liability-inducing terminology directly to neutral compliance phrasing, closing the final loop between physical hardware engineering and corporate legal defense. These 8 patents form the Sovereign Enclave, a unified architecture designed to enforce constraints from silicon validation up through linguistic compliance. In this architecture, violating data sovereignty requires breaking the fundamental laws of physics rather than simply exploiting a configuration drift. In an era of autonomous machine speed exploitation, software lies, physics does not.